Now we will consider another charge distribution where we have now the charge distribution uniformly over the circumference of a ring. And we want to find the electric field at the axis, at an axis passing through the center of the ring. Now we assume the ring is placed in this way. Of course, this is a 3D shape, so the ring is, think of it this way, so it is coming out of the page, and the axis is, I'm choosing to be along the x-axis. The ring has a radius a, and I want to find the electric field at a point P, which is at some x. X can be anything, and there is a charge distributed over the whole ring uniformly, and this charge is Q, so this means that lambda is Q over L. In my case, L is Q over 2 pi A, and this is in coulombs per meter. This is the linear charge density in this case. Okay, so we apply our algorithm. We have conceptualized the problem. We have drawn it. We have drawn the figure, and know everything now. Everything is clear. We have put the data that is given, and now we are ready to go a bit further. The first step is to identify what is dq. Well, dq is the small point charge that results when you divide the charge distribution into small elements. Evidently, in this case, dq will be just a small arc, the charge on a small arc of the ring. So the whole ring is divided now into these small arcs, and each one of these will carry its own dq. The electric field at this point will be the sum of the electric field over these dq's. So the dq is this. Let me pick up one of these dq's. It is here, and then start doing analysis before writing anything, thinking of what I will get. Now, dq here will have its electric field dE at this point. Now again, for definiteness, I take this dq to be positive. This distance is r, and so the electric field of dq in this case, which is dE, will be in this direction. So this is the first step. Now, I'm still under conceptualization. Okay, so it will be in this direction. Now, I look at the symmetry of the problem, which is the most important argument that I have to make actually before starting doing any calculations, to see what happens to the electric field when I add up the contribution of all these dq's. I note that, of course, this needs some experience, but you will eventually do that. I note that there is, for this dq, there is a dq across the center of the ring, which will contribute another field, call it dE prime in this case. Okay. Now, dq, this is dq prime. dq and dq prime, I'm assuming them to be the same because I'm dividing the ring into small infinitesimal elements which have the same charge. Now, this distance r prime, this is x here, this is r prime. This r prime is the same as this r. Actually, it is the same for all dq's on the ring from the geometry. Now, if you look, and so the dE here, this dE prime is the same as dE in magnitude. Its direction is different. However, what I note now is that if I decompose this dE prime, this is dE prime x, and this is dE prime y, and I have, this is dx, and this is dEy. Okay, I note that because of the symmetry and because this angle, the angle that this subtends here, call it phi, and this angle is the phi. Actually, it is the same for all dq's on the ring due to the symmetry. Then I see that the y component dEy and the y component dEy prime are equal and opposite in this case. And so they will cancel each other. Now, since when I try to find the electric field of the whole ring, I have to add up the electric field of all the dq's, then I can see that for each dq here, there will be another dq across the center of the ring that will contribute a field that will lead to the cancellation of the component other than the x component. Okay? And in this case, therefore, when I add up the contribution of all the dq's here, I will end up with a complete cancellation of the component of the electric field along the y direction, and the only component that will survive is the one along the x direction. Therefore, I need to worry only about dEx, the x component of each of dq, and then sum over all the dq's to find what is the total Ex. So this tells me, this symmetry argument tells me that the electric field of this charge q distributed uniformly over the ring will contribute a field, this q will contribute a field that will be along the axis of the ring, that is along the positive x direction in this case when the charge is positive. So this is the symmetry argument, and you do this before you start writing down things. Okay. Now, having done all of this and knew what you have done, now you move to the analysis stage. You try to analyze. And as we have done before, I write the expression for the quantity that I want to find, which is dEx, which is dE cosine, because this is phi, and this is also phi. Let me remove these components because I don't need them anymore, the prime components. Yeah, I remove the y component also here. Okay, I remove this, I remove this. So let me remove this to make things less crowded. So this is phi, this is also phi, and so this is dEx, which is equal dE cosine phi. Okay, and this is the component that I need to write down. Now, what is dE? dE is k dq over r square. So this is k dq over r square cosine phi. Okay, now the next step is express r. This is a general expression for the electric field of a point charge, this dq. Express r in terms of the coordinates of the problem. What are the coordinates? Now, this is x and this is a. So r square is x square plus r square. So this is k dq over x square plus a square. A is the radius. So cosine phi. This is dx. Now I can go further actually, and I know that cosine phi is just x over a again, or sorry, x square plus, it's cosine phi is x over r, so it's x over square root of x square plus a square. So this tells me that k dq x over x square plus a square to the power 3 over 2, where I have noted that from here that cosine phi is equal x over square root of x square plus a square. Substituting this here, you get your dx. Okay, so this is the expression for your dx. Now, the next step is to express your dq in terms of the in terms of the linear charge density. For this purpose, let me remove this. I note that dq here, what is dq? If you look at the ring here, this dq here is, as usual, the general expression is lambda dl. What is dl? Is the length over which, infinitesimal length over which dq is distributed. But what is this here? In this particular example, it is an arc. Okay, an arc that subtends, that is ds. Okay, so this is equal lambda ds. Let me keep it this way and then proceed. So it is the dex now is k lambda ds over x square plus a square to the power 3 over 2, and I have x, of course. Kx lambda ds over x square plus a square to the power 3 over 2. This is my expression for dx with dq expressed in terms of the charge density, and I have. Well, here comes the hint now. This is dx. I want to integrate now. Here, of course, once you see this, you get a hint about what is your integration variable. It seems that it is s. It's the coordinate along the ring. Now, let me write down the integral. Ex is just dex. You sum all of these, and it is integral over these. So it is k lambda x ds over x square plus a square to the power 3 over 2. Okay, now I want to find the limits of integrals and really what is the integration variable. First of all, you note that in this particular example, x is constant for all dq's. So it's not an integration variable. It is not a quantity that varies actually in this case, because all the dq's have the same r, so they have the same a and the same x from the symmetry. So x is not an integration variable, it's a constant in this example. K, lambda, and a are also constant, so you take everything outside the integral and you are left with this is an integral over ds. Okay, so integral over ds, what does it mean? Actually, it is a sum over all the ds's that form for you what? Form for you the circumference. So either you write the limit as 0 to 2 pi or just immediately here say that this quantity is just 2 pi a when you integrate it. In other words, when you sum these all ds's, you get 2 pi a. And therefore, I get for my expression, Ex is equal k lambda x multiplied by 2 pi a divided by x square plus a square to the power 3 over 2. Now, if you recall the expression for lambda from here, which is q over 2 pi a, then actually if you replace lambda with q over 2 pi a, this will cancel and the expression will be kqx divided by x square plus a square to the power 3 over 2. So this is your x component, and your e in this case will be just kq x over x square plus a square to the power 3 over 2 I hat. This is your electric field vector because it is directed along the positive x direction. So this is how you analyze the problem and come with a solution. Now we come to the checks. First of all, evidently, this is along the positive. This is a positive quantity multiplied by a hat because everything here is positive, so it is in the right direction. The second thing, the units. It should have dimensions of, as I said, k multiplied by Coulomb divided by length square. Now, this is length. This is length to the power 3 over 2, a over x much less than 1. in this case, E, which is KQX, you take x as a common factor in this case, so it goes like x cubed multiplied by 1 plus a square over x square. Now, this goes when a over x is much less than 1. You can ignore this now in comparison to 1, okay? And this reduces, of course, I have I here, it reduces, and this x will cancel, this cube will get square here, so k cube over x square I hat, which is the expression for the electric field of a point charge centered at the origin at a point x along the x-axis, and it is directed along I hat, given that q is positive. If q were negative, if the charge here were negative, then the only thing that would change is that the direction of the electric field. Electric field will be along the negative x direction. Okay? And this expression, as well as this expression, is actually valid for both positive and negative charge. Just substitute q here with its sign, and you will get the right expression.